Now first is, this fault is fed by two ways. First is, it is fed by this circuit breaker A, means the current will flow from the sending substation via via this circuit breaker A to the fault point F. Now what is the second way? Second way is, the fault is fed via circuit breaker B, then the circuit breaker Q, and then the circuit breaker P. Now see, in the normal condition, the power will flow from the sending substation to this receiving substation. So the direction of power is from sending to receiving in both the feeders. But when the fault occurs in this feeder, the direction of power flow in the second figure get reversed. See, the power will flow from B, Q, and then through P. So in this way, the power have to be flow from A to P, but now due to the fault, as the fault is fed by this this feeder 1, it is flowing from in the opposite direction, that is in the direction of the arrow. So in this way, this relay will get operate. So directly from the feeder 2 via relay A, and second from the feeder 1 via B, Q, and substation P as shown in the figure. So this clearly shows that the directional relay Q carries the current in the normal direction, whereas the directional relay P carries the current in reverse direction momentarily. So this operates the relay P instantaneously. So the relay A having the inverse time characteristics also operate because of heavy flow of the current. So in this way, both the circuit breakers A and P will operate, and it will disconnect this faulty feeder from the substation. Therefore, the continuity of supply can be maintained through the feeder A, feeder 1. Now, third category for the time graded protection is a ring main feeder. Now, this system in which various power stations or substations are interconnected by the number of feeders forming a closed circuit is called a ring main system. Now, in this system, the system of protection, non-directional overcurrent relays having inverse time characteristics are employed, whereas directional or reverse power are employed on the both sides of each substation. The minimum definite time of all the relays are set properly as shown in the figure. So let us first again revise. Here again we have two type of relays, non-directional relays and directional power relays. Now see, there are number of, now this is a generating station. Now here number of substations are connected to form a ring. So whenever the fault occurs on any of the section, only the corresponding relays will operate without disturbing the other relays of the network. Thus the faulty section is isolated and the supply is maintained. Now next scheme is, that is a differential protection of feeder. It is also known as Translay scheme. The Translay scheme is basically a voltage balance differential protection scheme, but in this scheme voltages induced in the secondary windings wound on the relay magnets is compared in place of secondary voltages of the line current transformers. The schematic diagram of a Translay scheme for the protection of a three-phase feeder is shown in figure on the next slide, and the relays used in this scheme are essentially overcurrent induction type relays. So, see, this is a diagram. Now, see, for as you know, for the differential scheme, the component which we want to protect is kept in center, and on the both side of this component we have to connect the CTs. So, this scheme is known as differential scheme. So, here we are doing the protection of feeder. So, we have a feeder, and on the both side of feeder we have a set of CTs. Here now the secondaries of CTs are given to the upper magnet of this relay, overcurrent induction relay. The central limb of the upper magnet carries a winding A or A dash, which is energized by the sum of secondary currents of the CTs placed on the feeder to be protected. The central limb of the upper magnet also carries a secondary winding B or B dash. See, B or B dash, which is connected in series with the operating winding C or C dash placed on the lower magnets. So, the connection from B is given to the lower magnet. So, both the B and C are connected in series. In between the two magnets, an aluminium disc D is placed, which is free to rotate. So, in both the magnets there is a disc which is free to rotate. Whenever EMF is induced in this disc, it is free to rotate, and when it gets rotate, the contacts of this trip circuit gets closed. Now, spindle of the disc carries moving contact which closes the trip circuit under the faulty condition. So, what will happen? Now, under the normal conditions, the current at two ends of the feeder are equal, so that the secondary current in both sets of the CTs are equal. So, consequently, the EMFs induced in the secondary winding C and C dash are equal. So, what so at during the normal condition, the incoming current from this CT, it must be equals to the outgoing current. It means the winding B and C dash will having the same amount of current. So, therefore, no any EMF gets induced in this disc. Therefore, so the EMF induced in the secondary winding C and C dash are equal and opposite, and no current flows through the closed circuited secondaries. However, when fault occurs on the feeder system, say at point F, now the fault is at point F, the voltage induced in C and C dash will no longer remain equal. Therefore, the current flows through this winding and the torque is developed in this disc. So, during the faulty condition, the currents in the two windings will not be equal. Therefore, this will this will provide the EMF in this disc. Therefore, this spindle will get rotate, due to which the moving contact of the trip circuit gets closed. So, therefore, the current flows through this winding and the torque is developed in the disc. Now, the central limbs of the upper magnet also carries a secondary winding which is connected in series with the operating winding C or C dash, which is placed on the lower magnet. In between the two magnets, an aluminium disc D is placed which is free to rotate. Therefore, the spindle of disc carries moving contacts which closes the trip circuit under the faulty condition. Thank you.